Hi, everyone. Thanks for the nice introduction and also thanks for the invitation. So as already mentioned, my name is Jan Wohland and I work at the Climate Service Center. We're just around the corner in the city of Hamburg. And our goal is to bridge the gap between climate modelers and users in industry or in any form of decision making. So what I want to talk about today is a wind speed stilling, and I will explain what it is in a second, and the recovery of wind speed stilling due to internal climate variability. And I chose the title because it's the same title as a paper that you can look at. It's given on that at the bottom. So it sounds a bit complicated, so let's start to unpack this. So what is stilling? In 2010, a group of researchers published an alarming paper in Nature Geoscience, finding that in a majority of weather stations in the Northern Hemisphere, wind speeds have been declining from 1980 to 2010, approximately. So what you see in this figure is every blue dot is a significant reduction in wind speeds between 1980 and 28. And those researchers concluded that if these trends continue, it's obviously really bad for wind power generation. Then there is some good news. A couple of years later, other researchers used the same data set, but there was more data available. And what they found is that after 2010, the trend has reversed. So they confirmed the initial results that from 1980 to about 2010, wind speeds indeed declined, but afterwards they recovered. And well, it's pretty obvious. This recovery is good news for wind park investors and the wind industry as a whole. So the big question, of course, is what happened in 2010? And are we going to see similar things in the future? And there are broadly speaking, two types of explanations for what happened in 2010. Some of them say something caused this change, and others say nothing caused it. So if you translate that into climate modeling language, the something means there is a forced change. So there's a trigger in the climate system, human activity of some sort that caused it, and nothing would be internal variability. So that means it's just the internal dynamics of the climate system which caused this. So you can come up with a lot of ideas what caused it. Some of them are land use change, even added wind parks themselves, which took away momentum from the circulation. So a lot of different possible explanation. And the other one is internal variability. And I will now show an example of how we can use climate models to actually show that it was internal variability. So what I did, and I'm not going to go into the details, I used a large climate model ensemble. It's called the MPI Grand Ensemble. It's 100 runs of one state-of-the-art climate model. So it gives you a lot of data. Each of these runs over 100 years or so, under past climate conditions and future climate conditions. And based on this data, I could show that stilling is internal variability. It's independent of the forcing, so it appears in the historic period, but also in the future. The trend amplitude in the climate models matches the trend amplitude that we see in the observations, and a couple of more technical aspects. So let me convince you that this is indeed the case. So what we have here is the so-called pre-industrial simulation of this climate model. Pre-industrial means they just assumed that from 1850, nothing happened. So no anthropogenic CO2 emissions, nothing like that, just continuous pre-industrial conditions. And if you do that and then evaluate wind speeds averaged over Europe, you get this blue line, and the 20-year mean is the black line. And the first thing that's obvious, this is not a flat line, it's going up and down. So we have multi-decadal variability in the wind resource. The second thing that's obvious, there are a lot of green and red dots here. And what they mean is each green dot is a starting year of a significant downward trend. So in each of these years that are green, a 20-year downward trend begins, and each red dot is an upward trend. And just by looking at this, you see it's a fairly common feature of the climate system to have these ups and downs. Moreover, the amplitude is also correct. So this is a histogram of the wind speed trends, the probability distribution of the wind speed trends, and orange is what the climate model tells us. And then the black vertical lines are what the observations tell us. And they match pretty well. As I said, this is for pre-industrial control, so pre-industrial conditions. I also did that for historical and future conditions. And I'm not going to go into a lot of detail here, but just convince you the distributions look the same. So this is historical, being 1850 to 2015. And these three are three different possible climate futures. And in all of them, there's a pretty good match. What you also see in green here, that's the climate change signal. And this climate change signal is a lot smaller than this internal variability. So you can see, for example, in the middle, the climate change signal is at the order of minus 0.03 meters per second per decade. But the trends due to internal variability are approximately 3 times as large. So that means looking at the next decade or 2, 3, 4 decades, the variability is more important than climate change. But then in the long run, of course, if we have these negative trends that are small, but if they continue until the end of the century because of climate change, then it becomes important. So let me wrap up. The research question was whether internal climate variability causes stilling. The industry question would be, can we expect these trends to continue, or do we have to expect up and downs? And what we found is that it's indeed internal variability that can explain the trends in the observations, and that climate change, so the forced trends, have a much weaker rate of change. And I would argue that has 3 different implications for applications. The first one is we need to expect ups and downs in the wind resource over multiple decades. And that also means that using 20 years of historical data is just not good enough. Second one, multi-decadal variability more important than climate change, certainly up to 2040, 2050 or so. And then the last one is, and that's more methodological comment, we need to make sure to better disentangle the variability and climate change, because often we only look at what does the model tell us for 2030 to 2050, but we don't separate what is forced and what is variability. And if you want to know more, feel free to just contact me. There's also a couple of other academic publications about this, which might be helpful. And yeah, thanks for your attention.